Hi, I'm Mark Barsamian. In this video, we'll continue our discussion of the definite integral and the fundamental theorem of calculus, and more specifically, we'll be discussing using the definite integral to solve what are called total change problems. This material is from section 5.5 of the book. More specifically, just a couple of pages in that section. Examples 5 and 6 are relevant to what we're doing in this video. The corresponding homework is this set of 3 exercises from section 5.5. Recall the fundamental theorem of calculus as it was first presented in the video for homework 78. The fundamental theorem of calculus, remember, is the relationship between definite integrals and antiderivatives. And it says this: if little f is continuous on a closed interval ab and capital F is an antiderivative of little f, then the definite integral of little f from a to b equals this change in capital F from a to b. And later in that video, we discussed change in f notation, and we used it to rewrite the fundamental theorem of calculus. So this definite integral, which the fundamental theorem says is equal to this change in capital F, could be denoted using change in f notation this way, and that could be denoted this way, highlighting the fact that the antiderivative, capital F, would be obtained by doing an indefinite integral of little f. In the current video, we'll be discussing total change problems, as I said a little bit ago. We'll start by discussing the fact that the fundamental theorem can be written in different forms. So consider the first presentation of the fundamental theorem from the previous page, that this definite integral of little f equals the change in capital F, the change in an antiderivative. Well, in this expression, the integrand is a function little f of x, and the function on the other side is capital F of x, which is an antiderivative. So in other words, capital F prime equals little f. Well, we could replace this little f with capital F prime in that integral symbol. If we do that, then we get a new version of the fundamental theorem of calculus. It's this version. The integral of the derivative, capital F prime, is equal to the change in capital F. It turns out that this form is useful for what's called total change problems. Notice that the right side of the equation represents a change in the value of capital F of x. We can denote that change by the Greek capital delta. So we write delta capital F. So this difference, capital F of b minus capital F of a, is delta capital F. So we see that what the fundamental theorem of calculus tells us is that the change in the value of a function equals the definite integral of the derivative of the function. The change in the value of the function is the thing that's on the right side of the fundamental theorem of calculus, and the definite integral, of course, is the thing on the left side. There are situations where one knows the derivative of a function and wants to know the change in value of the function. In application problems, that is, problems about applying math to solve some real-world problem, in those application problems, the known derivative will be a rate of change of some quantity. One will be seeking the change in the value of the quantity. That's what we'll call a total change problem. We see that the fundamental theorem of calculus gives us a way to solve that kind of problem. So let's set out the terminology of a total change problem. A total change problem will be a problem of this type. Given the rate of change of some quantity, and given two numbers, a and b, with a less than or equal to b, the goal is to find the change in the quantity. In the solution format is this: we find that change in the quantity by integrating the rate of change, using the fundamental theorem of calculus to say that those two things are equal. In this video, we'll study two examples of total change problems. The first example is similar to two of the homework exercises, number 69 and 70 from section 5.5. They're about marginal cost and change in cost. A company makes bikes. The marginal cost is this. Capital C prime is 100 minus x over 5 on this domain, where the variable x represents the number of bikes made per month. That is the quantity made per month. Question A is, find the increase in cost going from a production level of 200 bikes per month to 300 bikes per month. So the solution is to first observe that this problem does have the form of a total change problem. We are given the marginal cost, that is this derivative, and we're given two numbers, x equals 200 and x equals 300, that satisfy this inequality. Looks like I've got a typo there. And we're being asked to find the change in cost, this delta C. So we should solve the problem by using the fundamental theorem of calculus. So here's the solution. First of all, we denote the change in cost by delta C, and that's just the difference, C of 300 minus C of 200. And then we use the fundamental theorem of calculus to say that that change in cost is equal to the integral of the derivative of the cost, that is, the integral of the marginal cost. Then we use our formula that was given for the marginal cost. And then we use the fundamental theorem of calculus to tell us that this definite integral can be obtained by doing this calculation with the indefinite integral. And as before, I do the indefinite integral details off to the side. In this case, I did them down here at the bottom. There's my indefinite integral details box. So this indefinite integral, I broke off and did out there, and I brought the results back and put them in the same place inside those parentheses. Now note that the result of the indefinite integral is this expression, which is the general antiderivative, which is a function form. It goes back into these parentheses. The next step is to find the change in that function form from 200 to 300. And that's found by just simply plugging in 300 and plugging in 200 and finding the difference. Now notice that the indefinite integral, of course, being a function form, has a constant of integration, which goes back in when we put that function form back into those parentheses. But that constant of integration disappears in the subtraction step. So our final result is a number, this number 5,000. So there's no constant of integration in a definite integral problem. When you're finally done with a definite integral, the constant of integration goes away. So our result is this number 5,000. And so our conclusion is that's our change in cost. The change in cost is $5,000. Now some observations about this solution. Notice that in solving total change problems, the fundamental theorem of calculus is used twice. It's used here to relate the change in some quantity to the definite integral of the quantity. That was one use of it. Then the fundamental theorem of calculus is used again to relate the definite integral of a function to this expression involving the indefinite integral of the function. Another observation is this. Notice that the change in cost is equal to the definite integral of the marginal cost. That's an example of what was observed earlier about the fundamental theorem of calculus, what it tells us. The change in value of a function equals the definite integral of the derivative of the function. The third thing to notice is that when we find the indefinite integral of the marginal cost, that is, we integrate c prime, we denote the result of that integral with the symbol capital C, and it has a constant of integration that's a plus k. So capital C of x is this function form. It's the function form for the cost function. It's not the actual cost function because we don't know the value of k. But also realize the meaning of capital K. The constant of integration in this setting is the fixed cost, because notice in this formula for the function form, capital C parentheses x, when you substitute in x equals 0, you get C parentheses 0 equals k. But what does C parentheses 0 mean? That means the cost of producing no bikes. If you have to pay for rent on the factory, salaries for your staff, or whatever, you'll still have some costs even if you don't make any bikes on a particular day or in a particular week. So the fixed cost is this C parentheses 0, and it's the value of this constant of integration plus k. Now, we never do know that fixed cost. We've not been given that. But we can still determine the change in cost, even not knowing the fixed cost. Question B. Illustrate the result of the problem using graphs of the cost function and the marginal cost function. Well, let's think about our result. We found delta C. It was this quantity. That's going to represent a change in height on the graph of the cost function. Now, what is the cost function? Well, it's this cost function form where we don't know the value of k. Now, it's worthwhile to think about the shape of the graph of that function. Well, we're going to have to think about it because we've got to draw it. If you consider that function as an abstract mathematical function, it's going to have a graph that's a parabola because of that exponent, and it's facing down because of that minus sign. That means that there's going to be some value of x, say x equals c, that maximizes the value of the cost. Larger or smaller values of x would have smaller corresponding values of the cost. But considered as a cost function, this ought to seem puzzling because it would mean that if the company made more than x equals c bikes per week, then their costs would start going down. That doesn't make sense. Making a larger batch of bikes should always be more costly. So how can the cost function be a parabola facing down? The key is the domain. Notice that we're given a restricted domain. 0 is less than or equal to x, which is less than or equal to 400. That's the domain for the marginal cost, capital C prime. Well, that means when we integrate to get the cost function, it also has a restricted domain, 0 to 400. It turns out that the max in this function form, that max would occur at x equals 500. So the x value of that max is out of our given domain from 0 to 400. On that restricted domain, the graph of the cost function given by that formula is only increasing. So here you see the shape of that function. There's the graph of that abstract mathematical function. That's that upside down parabola. But you can see that on our domain, we don't actually ever reach that max. So that's an explanation of why the graph looks the way it does. Now, how do we illustrate the change in cost? Well, this quantity will show up as a change in the height of the graph. So I've shown that as a red arrow. Here it is. Here's the value of the cost when x is 200. Here's the value of the cost when x is 300. The difference in those two y values I've highlighted with that red arrow, and I've labeled it as delta C equals 5,000. Notice on this graph, the fixed cost shows up down here. That's the y-intercept. It's the cost when x equals 0. So the change in cost shows up on the graph of the cost function as a change in height. Now, what about the other symbol? This definite integral is going to represent a signed area of a region on the graph of the marginal cost function, C prime. Well, that graph, C prime, is going to be a straight line. Now, the abstract function, that's the straight line function, y equals 100 minus x over 5, that function goes on forever as an abstract mathematical function. But the marginal cost function has this restricted domain from 0 to 400. So our domain is that interval. And this definite integral corresponds to the region between the graph of C prime and the x-axis from x equals 200 to x equals 300. So that's this shaded area. And the value of that shaded area is 5,000. So that's how we illustrate the result using the graph of C prime. So the change in cost shows up on the graph of the marginal cost as an area. That's the end of that example. Let's go on. Example 2 is similar to 5.5, number 89. It's about bacterial growth rate and change in weight. A bacteria culture is growing at a rate W prime equals 0.6 e to the 0.2 t grams per hour. Question A is, how much does the weight of the culture change from t equals 5 hours to t equals 15 hours? And the instructions are give an exact answer and a decimal approximation. Now, I've worded this problem the way that the book words it. Notice that this is sloppy writing that's common in math books. Grams is a unit of mass, not a unit of weight. If you were reading this problem in a physics book, it wouldn't ask about the weight of the culture, it would ask about the mass of the culture. But anyway, you get the idea. Now, let's observe that this problem has the form of a total change problem. We're given the rate of change of the weight, that's that thing, capital W prime, and we're given two time values, t equals 5 and t equals 15. 5 is less than or equal to 15. And we're asked to find the change in weight, that is delta W. So we should solve the problem using the fundamental theorem of calculus. Well, here's the solution. First thing that we do is we write the thing that we're trying to find, this change in weight, and then we use the fundamental theorem of calculus first to relate that change in weight to the definite integral of the rate of change of the weight. So remember, the change in value of a quantity equals the definite integral of the derivative of that quantity. Then we just substitute in the formula for W prime. And then we use the fundamental theorem of calculus again to relate this definite integral to this expression involving an indefinite integral. And then we do the indefinite integral details off to the side. That is, this indefinite integral we break off and do out here in this indefinite integral details box, and we substitute the results back into those parentheses. Notice that the result of the indefinite integral is a function form. It has a constant of integration, and it's denoted capital W. We integrated capital W prime and got capital W as a result, but it's a function form. It has a constant of integration. And then we get to work computing the change in that function form. We substitute in t equals 5 and substitute in t equals 1 and subtract. And we simplify, and we end up with this expression, which is the exact answer, 3e cubed minus 3e. That's the only way to write that number exactly. This is a decimal approximation obtained by typing those symbols into a calculator. Now, for a MyLab problem, you're probably asked for a decimal approximation, and you're probably also told a number of decimal places to give. But just keep in mind that the way to solve these problems is to work in symbols all the way up to the very last step. Only at the very last step do you substitute things into a calculator. Now, a couple of other things to notice. When we do this indefinite integral, we use that indefinite integral rule. Remember that there's a pair of rules that's worth remembering together. One is a derivative rule, and the other rule is an indefinite integral rule. That pair of rules is useful to remember together. So notice, in this problem we have a k that's the number 0.2, e to the 0.2 t. So it's t in this problem, not x. So in the next step, we have e to the 0.2 t divided by 0.2, e to the kx over k. And then we had to do careful arithmetic. How do you divide 0.6 by 0.2? Well, keep in mind that 6 divided by 2 would be 3, so 0.6 divided by 0.2 would also be 3. That's how we get that 3. So our conclusion is that the change in weight is roughly 52.1 grams. Similar observations should be made here. Remember, the change in weight is equal to the definite integral of the growth rate. So that is, the change in value of a function is equal to the definite integral of the derivative of the function. That's what the fundamental theorem of calculus tells us. Also, observe that when we find the indefinite integral of the growth rate, capital W prime, we denote that result, capital W, and note that that has a constant of integration. So W parentheses t is this function form. It's not the actual weight function because we don't know the value of capital C. So it's a function form for the weight function. But realize the meaning of C in this setting. The constant of integration plus C is the initial weight of the culture. That is the weight at time 0, a weight that we've not been given. But we are still able to determine the change in weight, even not knowing the initial weight. Question B is to illustrate the result of the problem using the given graphs of W of t and W prime of t. Well, first of all, let's represent the change in weight on the graph of W of t. Now again, this is a function form. We don't actually know the value of that capital C. And I made a mistake. When I said that the value of capital C was the initial weight, I should have said it's related to the initial weight. When you plug in t equals 0, you don't get c as the value, you get 3 plus c. So again, the initial weight of the bacteria culture is 3 plus c. And that shows up on this graph here. It's the y-intercept of that graph. Now we're supposed to illustrate the result that we got. Our result was a change in height, delta W. That's going to show up as change in y values. And so here's the y value or the W value when t equals 5. Here's the W value when t equals 15. The change in height I've highlighted with that red arrow. In the length of that arrow is this number, 3e cubed minus 3, which is roughly whatever we said it was, roughly 52.1 grams. Now, how do we illustrate this on the graph of W prime? Well, this change in weight we found by integrating the growth rate. And so if we have a graph of the growth rate, as we do down here, these curves have a similar looking shape, but they're not the same curve. This is the actual growth rate. There is no unknown constant in this formula. And so we see that the initial growth rate is 0.6. And this definite integral represents the value of the signed area of the region between the graph of that growth rate function and the t-axis from 5 to 15. So this area that's been shaded red. So the number that's the change in height on this graph is the same as the number that's this area on this graph. That's the end of that example, and that's the end of this video. Thank you.